Hi everyone, welcome to the last seminar of the semester. So our first speaker tonight is, it's almost night, yeah. This afternoon is Matt McGill. Matt received his BS degree from the University of Rochester in 2009 and the MS degree from UIUC in 2011, both in electrical and computer engineering. He's currently a PhD candidate under Professor Krein with a research focus on electric machine design. He's held electric machine internship positions at John Deere in Dubuque, Iowa, and GE Global Research in Schenectady, New York.
All right, thanks, Ming. Is this too loud? That wasn't electric machines. Can you turn it down a little bit? So my talk today is stator configuration constraints on electric machine performance. Is it better now? Okay. So this talk, I started this work a year and a half ago, and then kind of got sidelined during internship, and just kind of picked it up this past semester. So first, let's talk about why we're working on the project. Then, because most of the people in this room don't work on electric machines, I'll kind of go through what's a basic design procedure you would go through if you're given, let's say, power as your operating requirement. And then I'll give a few definitions that I'll use later on to kind of define my research. And then I'll talk about why we're looking at it and what can be done. So my research is focusing on winding design for inverter-driven machines, not line-fed machines. So it's not only 60 hertz. The machines I work on are only used with inverters. And then, of course, conclusions. So most people think electric machines are kind of this very mature technology, which has been around since 1884 when Tesla invented it, which is very true. I mean, like, the machine itself hasn't really varied too much, but since we introduced power electronics in the 50s, 60s, and 70s, it kind of changed the whole operating scheme of things. So probably since the 80s through today, there's been a lot of work on kind of changing machine design for use in inverters. And a lot of that work has been focused on the shape of the rotor. So this one right here is an IPM machine. So this machine can only be used with an inverter. So this is an example of something that didn't even exist in the 70s. Most of the work is done on kind of changing the shape of these stator slots, changing the size and the dimensions of the rotor magnets, the rotor gaps, things like that. And also for an induction machine, you kind of tweak the slot shapes. But not really much work has been done on the stator windings, which is really our only connection to the machine. Right? We either supply a voltage or a current into the windings, and that creates a magnetic field. So that's kind of what made us wonder why has no one else really looked at this before. And I found that it's because it's a very complex topic where when you start designing, you usually just look at a table that says if you want, say, to go this fast and you want to have this much power, just choose this winding ratio and it works. It's tested. Everybody knows it. So it's kind of one of those things that you have a lot of designers using the same handbooks. Like, why question it if it works? So we're, I guess, trying to start questioning that. So this is a quick primer on induction machine design. So what you can start out with is called a sizing equation. So if you're given the amount of horsepower that you want your machine to have, you can use this long equation here, where each parameter is, a massive equation that has to do with the rotor structure and the stator structure. But basically, what you care about is this d squared L. So the power out is proportional to the diameter of the machine times the length of the machine. So that's why it's called the sizing equation, because it kind of gives you the volume of the machine you're working with. So once you kind of have the volume, then you start working on the stator and rotor slot shapes. And in the stator, you, in addition to the rotor, where you can only mess around with the slot shapes. In the stator, you have, of course, all the windings and how they're interconnected. So that's what I'm going to focus on. So just a quick definition. A coil is just a loop of wire, has end turns, and has a go and return coil side. And the coil sides are separated by the pitch or throw, or some people call it span as well. So that's another thing that's confusing in machines, is that GE uses, let's say, pitch, and Westinghouse uses throw, and another company uses span. So if you look at a paper, you might not even understand it because the terminology is completely different. And people in Europe use the terminology that's even different than any other company in the U.S. So this example here, the way I'm defining in this work, whenever the current goes into the page, it's called the go coil side, and coming out of the page is the return coil side. So a winding is just an interconnection of multiple coils. It can either be just one coil, or it can be two coils in series, two coils in parallel, any combination between those two. And most conventional machines are M phases, or usually in our case 3 phases, where these windings are symmetric and they're just displaced by 2 pi over 3, or 120 electrical radians throughout the machine. So right here I have just a phase A winding drawn here. It's a 4-pole machine, right? You have 4 magnetic poles, and there's actually 8 different coils. So if I take the 8 coils for phase A and connect them in this arrangement, where I connect these 2 on one pole in series, and in parallel with these 2 in series, and connect them in series with these over here, that would create my phase A winding for my machine. And this is a very conventional way to do it. And the reason why you connect them in series and parallel is to kind of mess around with your voltages and your currents. So whenever you add multiple coils in parallel, you're going to be splitting the current, right? And whenever you're adding multiple coils in series, you're going to be summating the voltages. So like in a generator, if you want really high voltages in the output, you'd add all your coils in series. So this is only for phase A. And you have the same thing for phase B. It's just phase shifted by 120 degrees. So now you have this second circuit, phase C, the same exact thing. So this is how coil design usually goes. So this is kind of where I define my problem, is that right now, let's say we're given, whenever we want to design a machine, you're given your performance requirements. Let's say your torque speed curve. Let's say I'm sure most people in 568 know the torque speed curve. Let's say you want.
We hope most people in 330 know the torque speed curve.
And 330. All right. So you have the torque speed curve or your performance requirements, and also most requirements also say that you have a balanced 3-phase source. So once you're given those two, really the only thing you can play around with is how you connect the windings on your stator, and that's it. So in some conditions, let's say you're operating as a generator in a 7-phase system, you might want to minimize a certain harmonic, like the 13th and 15th harmonic. Or in your 5-phase system, you want to minimize the 5th, or you want to minimize the 9th and 11th. So those are kind of tricks you can play with that based on your system. So if you now instead remove this balanced excitation requirement, and your only input is just your performance requirement, say torque versus speed, or power, or torque density, or power density, you kind of open up your design space. So now, given that performance requirement, you're looking for a combination of inverter and output voltages or output currents that can give you that performance. So kind of opens things up. And here I kind of show that it doesn't have to be balanced and it doesn't have to be symmetric. So you can have, let's say, phase 1 is a sine wave, and phase 2 is a sine wave with induced harmonics to do a certain something like inside your machine. So essentially what we're asking here is that can an inverter be used to create any arbitrary air gap field inside your machine? Is because what you care about is magnetic fields, because if you match magnetic fields, then you match the torque and power output of any machine. So this is an example I took from a paper. It's a conventional concentric winding design, and this is only phase A. And I just input all the winding configurations in a program I wrote, and out comes a magnetic field throughout the air gap. It's missing units, but it's Mac to PC. So the question is, can I take this conventional machine?
On the Mac.
Yeah. Mac. Yeah.
What about PowerPoint?
This is Mac. Yeah. Yeah. So the question is, I have the performance of this conventional machine. So can I, let's say, create this different winding and form the exact same magnetic field? So in this winding, you have one excitation around every single tooth. So this is a 24 tooth machine. So that means you have 24 different inputs coming from your inverter. So instead of 3 phases, you have 24 phases. And then another, so this winding is called a double layer concentrated winding. And that's just because in every single slot, you have 2 layers. So another option is a horrible drawing, but it's called a full pitch winding. So since this is a 24 slot, you only have 12 excitations now, where each coil goes all the way across the entire machine. So this one goes all the way over and goes back in there. The next one goes 12 slots over there. So the question is, can I also formulate this? Because the different coil shapes will give you different performances for your overall machine. So how we look at this problem is just doing harmonic analysis of each separate coil. This equation is not really needed, but what this equation is saying is that the inner summation is just the Fourier series of the magnetic field created by any one of those coils. And then this outer summation is just summing all of the magnetic fields created by all the coils. And so to allow superposition, you have to assume that using linear magnetic material, which in the real world isn't very true, but it's research, right? It's a starting point. So the initial problem was that I'm given this MMF or a magnetic field curve, and I want to create it in here. So one way you can do that is just creating a simple linear system where your system matrix A has to do with how your coils are connected throughout your machine. The X is what you're looking for, so it's saying in each one of these coils how much current and how many turns do I need to do, or how much current do I need to supply into it. And B is saying, given this curve, how much MMF or how much magnetic field is created by each slot. So if you just solve this system in a per slot basis, you can solve for the currents that are required. So this just provides some results for this. The blue curve here is called unconstrained. The red curve is constrained. It's also Mac PC issue. Yeah, sorry about that. This plot is it's harmonic amplitude, and this is harmonic number. So I found out that this machine can in fact create the exact same blue waveform as the other one, but what it requires is about 3.5 times as much current per slot as the conventional design, and that's just because none of the waveforms are overlapping each other. So this winding here only provides flux in this tooth, and this one here only provides flux in that tooth. So whenever you want to create really high flux in one region, the tooth in front of that part of the air gap has to have really, really high current to provide that large flux. So then you could say, well, what if I don't want to have this really, really high current in my stator? What if I want to, say, put it at 1 per unit? You can solve a nonlinear optimization problem where you're adding a constraint. It says, the current can't go above a certain level, and that'll give you this lower curve. But basically, all I want to show here is that you get the same waveform, just the amplitude is reduced. So it's the same characteristics. So now this is another option. So it's the full pitch machine I was looking at. The first test was to match the blue curve, and that was done successfully. But then, just because of the arrangement of this winding, it allows you to operate in not only a 2-pole operation, but you can operate in a 6-pole or a 10-pole operation. So, which isn't possible in any other electric machine. Like once you wind it as a 2-pole machine, it's always a 2-pole machine. Or if you wind it as a 6-pole, it's always a 6-pole machine. So this plot here is just showing the blue curve is the MMF when you're operating this as a 2-pole machine, and the red is when you're operating a 6-pole machine. So the drawback is that even though you have the exact same current per slot, the MMF in a 6-pole is much lower. It's about 3% lower, or 3 times smaller. So you're obviously have a trade-off there. But that's something that's only possible by having 12 different excitations instead of 3. So these are just more possibilities, kind of a review of the possibilities if you connect an inverter and use an inverter in your design process. So one is the electronic pole changing, which I just talked about in the last slide. And what that allows you to do is, if you say are in an electric vehicle where your speed range is very large, say from 0 to 10,000 RPMs, you'd want to operate in a high pole count at low speeds and a low pole count at high speeds. So that allows you to minimize how much your frequency from your inverter is varying. So that can help in optimization purposes, because it's very difficult to optimize a design over a wide operation range. But if you kind of minimize it, you can create a better design. Another thing which I think is pretty interesting is electrical load damping. So whenever you have magnetic fields that are rotating inside a machine, you're going to have forces in the tangential direction, which is causing torque, but you're also going to have forces in the radial direction. It'll cause noise, which Tuku, you know that, over in the lab. You're going to have vibrations, which is the radial forces of the pressure inside the air gap. But what you can do here is that since we have better control of the air gap fields, we can induce different mechanical modes or pressures throughout the machine. So like an application for this is like an electric vehicle. If you're changing gears, that'll put a mechanical force on the shaft of your machine, which you can hopefully balance out by changing your excitations. Another is improve fault tolerance, and that's just because the more excitations you have, the more ways you have to kind of compensate for a failure. So if you say have the exact same winding structure in 3-phase and 6-phase, that 6-phase gives you twice as much redundancy. So that's often done in aviation. And the high precision control. So it just allows you to have very precise knowledge of the fields inside your machine. So conclusions, I just basically stated that most aspects of the electric machine have been reevaluated for use with an inverter, but the stator windings really have not. I provided some simple winding structures and show that you can have the exact same performance with these different windings, although there are some trade-offs. I highlighted some potential performance improvements that are only guaranteed or granted if you can have electronically configurable winding. And right now I'm working on dynamic simulations, because all these are steady-state simulations and it's assuming linear material, but now I'm doing dynamic simulations of pole changing. So actually switching from 2-pole to 6-pole during normal operation. All right, thank you. Yep. That's Ruby.
So that's a good presentation.
Thanks.
Aside from the fonts and stuff.
Yeah, it's not my fault.
Yeah, it's not your fault. Do you see much efficiency improvements here?
I don't think so. I think this is like one of those applications where it's say you don't really care about efficiency right now. You want really high performance in one region. So like one of these designs, like this design, is going to be a really short machine. This one here, because the windings have to go across 6 slots, you're going to have many coils on top of each other. So the actual size of the machine is going to be like 150% of what the magnetic part of the machine. So it's actually really big. So this one would be almost a third smaller. So in some applications, that's better. Size is better. But I don't think efficiency I think that'd be
You
tough.
don't think these will be more efficient?
I don't think so.
But if you get the weight down, then
Yeah, it's possible to be maybe more torque dense, something like that. But I'm not sure about like efficiency or other like that kind of performance.
yeah, because weight could be an issue in like aviation.
Yeah.
I mean, the good thing about your presentation is that it's like the takeaway is sort of getting excited about winding design, which, you know, probably most of us are not
Yeah.
excited about. I mean, you're conveying that in a good sort of way.
That's good. Well, it took me 2 years to be excited about it.
Well, yeah, I mean, you seem like you can convey, whether you personally are or not, I don't know. But it's like you're conveying it about.
All right, thanks. Carl?
So just a couple of questions. One is that, I mean, the equations you use to drive those curves are fairly simple.
Yeah, yeah.
Now, if I were to actually take that machine design, go to the next slide, and the oscilloscope would actually get that curve? Or
Yeah, yeah.
Without having to do a fancy finite element analysis?
Yeah, you will. Oh, like it's not going to be a sharp top like this. You'll have some other harmonics, but yeah, you'll see something similar. You'll definitely see a staircase function. Yeah.
And related to this, we talk about efficiency. Now, I gather what you still have is the same fundamental energy density of the machine. All you're doing is you're kind of tweaking it around that energy.
Mm-hmm.
Because in order to improve efficiency, you need to
Reduce losses.
reduce losses.
Yeah. So, like, the research I'm working on now isn't really, I don't have like a goal that's like, say, take a 10 kilowatt machine and maximize this or reduce this. It's kind of saying, you have this inverter and it can do so much, and you have this machine that could do so much as well, but right now, we aren't really designing the machine for this really, really flexible inverter that we can program to do whatever we want. So it's kind of just exploring and saying what's possible. And I'm having a real hard time finding an application that warrants this. Like,
Because it would be expensive.
yeah, it's really expensive. So like this would take 24 like H-bridge inverters, where who would want to like build that? What company would want to have that in their vehicle instead of just 3 phases? 6 switches.
Well, maybe I misunderstood what you said, but did I hear you say that you can dynamically reconfigure the winding configuration using a power source?
Essentially, so if you have each one of these, like this is just this example, if you have each one of these separate, so you have, let's say, a DC voltage coming in, and then you have H-bridge, so this can be either positive VDC, 0, or negative VDC, then you are putting whatever current or whatever voltage you want in each one of these separately. So that's the same as reconfiguring like the winding.
So in essence, you could create a machine like a transmission where you vary torque speed curves dynamically on the fly. And so it seems to me, just an electric car, for instance, have application.
Yeah, but I mean that's true, but like an electric vehicle, you're limited by your mechanical structure, so it's something that is always going to kind of get in the way. Christine?
Do you have the same number of coils as slots? Like, what are the dimensions of
A. So A is going to be an I by J. So it all depends on how you want to wind it. So if you wind it this way, you're going to get J by J. So it's a square matrix. And this one is going to be I is 1/2 of J. Yeah. 2Q.
So have you actually looked at what speed range, what kind of pole count would give you a maximum torque over white space?
No. It's something that once I get a simulation working.
So also the dynamics, flux dynamics while switching between pole count.
Yeah, I think that's going to be pretty challenging. So people in the past have done their PhDs on switching between 2-pole and 4-pole, 2-pole and 6-pole, but it's all mechanical. So it's actually kind of winding a machine as a 4-pole and then making it a really crappy 2-pole machine by putting in contactors. So this is you are making it a really good 2-pole, and you're still making a pretty good 6-pole. Like the harmonics are nice. It just can't have as much torque as a 6-pole machine. So, I mean, I haven't really done any more than this right here.
Is it possible that not eliminating gearbox out of you doing
So that's.
is that like a goal?
I don't think so. No. So like if you're like talking like electric vehicle, the motor would have to spin really slow. Right. So I mean, it all depends on your application. All right. One more question, Trevor.
Yeah, kind of like a general design question. Like in 568, we were talking about like a lot of times inverter is your limit on what you can put the motor to.
Mm-hmm.
Even like if the motor is rated to like 10,000 RPM, it always seems like, well, you know, it can go higher than that. I just from designing a machine perspective, like how is that rating really set?
The mechanical?
Yeah.
So you do a mechanical analysis on the rotor. So I think Professor Klein mentioned in class the other day that this machine here, it's called the IPM machine, where you have chunks of magnet.
Yeah,
So yeah, when you spin it fast, the centrifugal forces are pushing those magnets outward. So like here, the magnet or the rotor is going to expand outwards, and then here it's not going to expand out as much. So whenever you have one part expanding more than the other, you're going to get lots of vibrations and more pressure, and then your reluctance is changing, and it gets really messy. So it's really a mechanical analysis that sets the speed, not the electrical. I mean, maybe the inverter will, like the switching losses, but it's mostly mechanical. All right, thanks.
Oh, which one is forward? This is forward, right?
Yeah, it's forward.
And this is light.
Yeah, I think it didn't work sometimes.
Maybe I should stay on the other side so I can see the clock. What happened? Huh? This is on the first page. Oh.
Yeah, our second speaker today is Max Liu. Max was born in Taiwan and he came to the U.S. in 1999. He graduated from Missouri S&T in Rolla, Missouri in December 2011. And he currently works with Professor Overby on smart grid-enabled distributed reactive power support, and he will continue his PhD next semester. His hobbies are figure skating, magic tricks, and traveling.
Thanks. Good afternoon. I see everyone is very happy because of pizza. So today my topic is smart grid-enabled distributed reactive power support with conservation of voltage reduction. It's a very long title, I know. And my advisor is Professor Overby. Okay, to give a little bit outline of my presentation, I'm going to talk about the background and motivation, and I'm going to give you a little bit review about reactive power and the importance of the power system. And then next one, I'm going to talk about conservation of voltage reduction, as known as CVR. And lastly, I'll show you some simulation results, and if you have any question, I'll be happy to answer them. So first one, I want to talk about a smarter home in the future. So this is from GE Target Net Zero Energy Home by 2015. And as you can see, it's a net zero, so it's like our new EC building over there. So the research topic I'm working with is actually using a smart meter and a solar photovoltaic panel over here. Of course, there's going to be some other thing like a battery storage, and there's going to be a wind turbine. But for my research, I'm focused on the solar energy and the smart meter. And this smart meter will have two-way communication between the end user and the control center, like distribution energy management, EMS. Okay, so next one, I want to show you the example of household loads. As you can see at your home, most of the load, the reactive loads are your heating and air conditioning, dishwasher, refrigerator, dryer, and vacuum cleaner. And usually those reactive loads are motor load. The biggest one is actually the heating and air conditioning. It can go from 500 to 2,250 bars. Also, on the other hand, you have a reactive source. And those source you are not actually, it's not under the current regulation, it's not okay to provide the reactive power support with those, because I think IEEE 1574 say you can only inject active power to the system. But if you were able to control the power electronic, the inverter, and the power factor correction device, you can actually have the computer to provide some reactive power support, the TV, the washer, the lighting, and UPS system. Now, however, on this paper in 1998, the author did not include the solar panel because he didn't think the solar will be a huge impact in the future. But average in the house, if you want to install a solar panel on your roof, the rating of the solar is usually 3 to 6 kilowatt. And usually the inverter of the solar panel has to be rated on its peak sun condition. So it means that most of the time, practically, you will have some reactive power support from the solar panel inverter. Of course, there's some other loading like resistive load, like a heater and incandescent lighting, oven, toaster. They're just resistive. So I'll give you a little bit statistic on solar energy. So if you can see from year 2000 to last year 2012, the solar energy globally going from like 4 megawatt installation to now you have a 3,300-ish megawatt installation around the globe. And now U.S. participation in percentage is on this solid line, and you can see we're going from like a little dip in 2003, but 2 years ago we started to see a dramatic growth of the solar installation. The reason is because the solar panel become cheaper. So if you can compare the price 3 years ago to now, I think the solar panel is 10 times cheaper. And because the silicon is cheaper, and we also have mass production in China, so bring the price down a lot. So why solar energy? Like I say, that it's one of the fastest growing renewable energy resource out there next to the wind. However, wind turbine is just so big, and if you're gonna put it in the residential neighborhood, first, it's going to be huge. Second, it's not very doable. But if you think about the solar panel, it's just really, really easy. You can just put it on your roof, and it's 3 to 6 kilowatt. It's easily can be done. And 78% of the existing PV for grid connect applications, like you can actually, if you have excess amount of power, and you can send it back to the grid, and then you can reduce your energy bill. In the end of the month, you actually get cheaper. You save money. And like I say, technology improvement and price reduction of the solar panel. So now the return on investment is 5 to 7 years compared to 15 to 20 years ago, 15 to 20 years, couple years ago. And lastly is the environmental awareness and greenhouse gas emission reduction. Like Professor Professor Gross always say the power system is a game for politicians to play. So energy sector is always going to be there. So I think the solar panel will going to get a lot of attention in the future. Okay, so I just want to show you a simple diagram to show how the power flow in the solar energy. So eventually sun shining on the module, then the inverter going from DC to AC, then fetch your house, and if you have extra amount of energy, the smart meter goes through the smart meter and then goes through the grid. And my research is actually focused on the smart meter here and the inverter over there. So let's talk about the PV inverter. So you can see the inverter actually operate in two quadrants, this quadrant and this quadrant, first and fourth. So we have 5 different modes I specify over here. And under the current regulation, we are only allowed to operate in mode 1. Like I said, we only allowed to inject reactive power, active power to the system. So if you want to operate in mode 2 or 3, this is more like an inductor. You absorb the reactive power, and this is more like a capacitor is injecting reactive power back to the system. Of course, mode 1, 2, and 3 are most likely going to be operating in the daytime, while mode 4 and 5 are in the at nighttime because there's no active power from the solar. But however, the most important equation here is you have to follow the S squared equals P squared plus Q squared. So this is your constraint over here. So why reactive power is important? Well, first because we use that to control the voltage in the transmission system. And then it impacts the system security and operation. And also reactive power support can decrease the real power loss along the feeder and the transmission line. And lastly, reactive power support can increase generator real power production and minimize the opportunity cost in the system. So take-home message is reactive power is very local and need to be dispersed throughout the network. So because my research is distributed reactive power support, it's very local. Therefore, I think this is a good application for this. So this is just an example done by Kay Rogers 2 years ago. And she published a paper. Actually, this is a voltage collapse prevention. This is before, this is after. And what she did is coordinate thousands of houses which has reactive support and ask them to inject at the same time. So you can see this is you can see the red color here. It means very dangerous, like emergency voltage. And after the injection in 5 buses, like 5 substations, you can improve the voltage profile dramatically. And this can prevent the blackout if you do this correctly. So next topic is give you a little bit idea about conservation of voltage reduction, as known as CVR. So, pardon me? Oh, no. Oh, conservation voltage reduction. Sorry. And this one is actually I took it from the residential ZIP model on IEEE 13 node system. So if you're not familiar with a ZIP, it's actually constant impedance, constant current, and constant power. So you know that when you reduce the voltage, the power consumption is P equals V squared over R. So if you have a purely resistive load, that will impact the most. The next one, if it's constant load, P equals VI. So if you reduce the voltage, you reduce the power consumption. So this one actually is a simulation I took going from 1.04 to 0.998. And you can see the power consumption is directly proportional to the voltage. Now, however, you might ask that this is the voltage and this is power. How about the energy? Because if you have a resistive load like your heater in your house, then if you set it to a 70-degree temperature, now if I increase the voltage, it might reach 70 degrees really fast. But if I reduce the voltage, it's still going to reach 70 degrees, but it might take a longer time. So in the end of the day, that you might argue that the energy is still the same. You're not saving the energy. But a result, a report done by EPRI actually showing that this is actually energy here. So they did on freezer and on TVs. So you can see that as the voltage decrease, your energy consumption is also decreased. But also this, I want you to take a note, this paper is in 1982. Since then, a lot of a change has been, the loading changed to the power electronics. So the validation of this is really, I cannot find any current testing on this. But the argument I might say is the efficiency, for example, for the motor, that if I lower the voltage and I apply different torque on the machine, and you can see the efficiency here in percentage actually can improve if I lower the voltage. So this is something, it might be good if your load behave like this, then you can say the efficiency improve and therefore they save the energy. Okay, so this is a little bit diagram to show you how the control and the optimization technique can be done. So the power flow is actually can go from distribution network and each individual house. And each individual house will have a smart meter that communicate with the distribution management system center. And also, there will also be communication between the distribution center and the distribution network to give you a full system feedback. So this is the IEEE 13 node feeder system, and you can see the little PV here. I put in 9 different nodes. I give a PV reactive power support. Now you might ask, why don't I put it everywhere? But the reality is you're not going to have a solar panel everywhere in the system. So I just be more realistic. I put it in this 9 different nodes. And my optimization basically is constrained nonlinear optimization problem. The VK here is defined as individual nodes of the 13 nodes. And my VK control, in this case, I set it to 1 per unit. And of course, your state is your voltage and current. And your control variable here is your injection, the reactive power injection to the system. And the equality constraint, your power flow equation, and your inequality constraint will be the one I showed you earlier, the Q max equals the square root of S squared minus P squared. So just want to give you a reference. This is a power flow equation here. It might not look familiar to you because this is in distribution. Because in distribution, usually is a radial network. You don't use the Newton-Raphson because it might produce yield condition matrix in that case. Okay, so sorry, 1 second. So once I reach the 1 per unit control here, I need to perform my CVR. So I will set the voltage to the lowest possible on the feeder. So in order to do that, this is already implemented in the system. So you can see that you have a control center, you have a LTC here. Basically, this will sense the voltage in the last house of the feeder, and accordingly to the voltage here, the tap transformer can set it to the lowest possible voltage. In this case, it's 0.95. So this is the simulation results that the green dot, a green line over here is actually the voltage before the CVR. Is a 0.99 here? It's close to 1. It's not really 1 because I do not have reactive power support on every single nodes. So this is the best I can get. And then after that, I use the tap transformer to set the voltage to the lowest possible, to which is do not violate the under voltage, which is 0.95 here. And this is the result after it. And I show you the numbers. So before no CVR, the substation is 1.037, and you can see your loading is 2,680, and your loss is 2.04. On the base case, you just perform CVR, then you can just bring down the voltage to 0.99. You save roughly 60 kilowatt energy here, but you increase the system loss because your current is higher by reducing the voltage. Then if you perform like a loss optimization function, then you can bring down the substation voltage to 0.96. However, you save further by like 2,618, but your losses dramatically improved to 1.58. But lastly, to my research, I performed the distribution voltage support. I can further bring my voltage down to 0.956, and my loading now become 2,613, and the energy, the losses savings become 1.75 compared to 2.04 before. So the take-home message is by doing this, I not only reduce the power consumption in the substation, also I improve the system loss profile compared to the no CVR case. And this is the result of the number of the IEEE 13 node system. And so for the future research direction, I'm planning to use, because right now it's centralized control, as you can see. So I plan to use less communication. Maybe it has a decentralized and centralized scheme, so to save the communication cost. So any questions? Thank you. Yes, Christian.
When you say distributed voltage support in that last row,
Yes.
what are you referring to?
Oh, I'm referring to this research, distributed reactive power support, basically, because I control the voltage. Yes. When I say distributed, okay, the word distributed means now my reactive power source is not just at substation, because now the currently just at substation, right? So now when it's distributed, it means your house, my house, everyone's house can inject reactive power there. That's the word distributed mean. Yes, Professor Pilawa. Different, you mean this? The tape. Oh, okay. Oh, this one?
Yeah. So as far as I can tell, the only loads that will give you, the only loads I can see that give you energy savings by reducing the voltage.
Okay.
Seems to me to be the electric motors that are not powered by an inverter.
Okay. Okay.
Water heater will just run for longer. It will take
Yes.
the heat water.
Yes.
The light poles will certainly, yes, energy will be introduced, but you have dimmer lights.
Mm-hmm.
Your oven will just take longer. Your toaster, I guess you'll eat a cooler toast.
Yeah.
So I'm interested in particular looking at the reactive loads as well, right? The dishwashers, refrigerators, and those things. Are those typically today using an inverter? I'm asking this because this follows very nicely to the math proof they found. Looking at his take on this as well, right? Are those inverter driven, or are they cheap ones?
Well,
driven by induction machine?
the one over here is actually, I don't think it's an inverter included because they do not have reactive power sources there. So when I say reactive power source, it means those loads has power electronic in them, so they can do power factor correction or whatever to provide reactive power.
You have the dishwashers.
Here?
The HVACs actually are
in the reactive sources today, or what percentage of them actually are
From the
machines?
from this paper, actually, it does not have it does not include it does not say it has reactive power support.
Yeah,
But it's like 1998, so I'm not sure about now. But
Recently, those top three actually have PFC circuits in the front end.
you mean this three
Yeah, those three.
has what?
Dishwasher, refrigerator, they all have PFC circuits to also be able to supply reactive power or accept the reactive power, so low to zero.
Okay, so they do have the.
What was that?
The first three
Some
have.
of the first three right now already have PFC circuits in them.
Yeah, I wonder what percentage. Do we have any idea?
I have no story.
Good as steers, I guess not steers.
I think most HVAC, like residential HVAC is still direct line. They're headed towards the direct average cost, but like what hits the home is still majority.
But they don't do reactive power support, but they actually cancel out.
Yes. Yeah.
Are you asking whether conservation voltage reduction is valid, or are you asking whether we can get more
I see the benefit if you have a peak load of power. If you want
Yeah.
to quickly reduce the power, then this sort of does that, right?
Yes.
But my concern is that most of these loads that will see the benefit, people will just buy a few more light bulbs because suddenly lights got dimmer. They'll up the rating of their toaster a little bit because the toast is getting cold.
Yeah. But I think the argument is coming to the efficiency. Like if you lower the voltage, maybe you can improve the efficiency. Efficiency sound like a machine load.
Well, but that's my point. The only one I see that happening is the electric machine that directly appliance connected.
Okay.
See, your argument is sort of an argument that I've made, and I've been talking to Richard a lot about this, and there are utilities that are saying that they get benefit from conservation voltage reduction. And I've sort of had the view that you have that I don't think so, but they seem to say that it's out there. In talking with Richard, one place I see where there could be benefit is if I'm selling an air conditioner and I'm going to go Best Buy, that air conditioner is going to have a rating on it that says how energy efficient it is. Okay, and you're the consumer. You walk and you pick the better one. Where did that rating come from? Somebody tested that unit at some voltage. So if you're the manufacturer and you knew your unit was being tested at a particular voltage, what voltage would you optimize for?
Yeah.
So if I'm tested at 120 volts, now I don't know what the testing voltage is, but if that were my testing voltage, I would optimize my unit to work best at that voltage. That would make sense. So if we can get that best voltage to those units, that would seem to be the most efficient. How valid these curves are, and Richard gave me this report. There was an EPRI report too that went with it, and I said, well, that's 1982. How valid is it? But the utilities are saying there's benefit in doing this, so we're looking at it. I don't know. I mean, I'm not fully convinced.
I agree. I've seen the numbers too, and you see a few percent improvement. I'm wondering if it's sustainable or people will start adjusting and install a few more lights.
Well, yeah, I agree with on the lights because I think you're just kind of, you can't, I mean, it's sort of saying, can you fool your customers? But incandescent lights are phasing out, so let's forget about that. So I'm not sure, but it's something to consider. And I know a lot of utilities are interested in CVR stuff, but yeah.
Yes, Guy.
Do these voltage reductions reduce the longevity of those appliances in the house?
Pardon me?
Does it have any impact on the longevity of the appliances?
I don't think so, because usually if you stay in the range of the A and SI, you should be okay. Because this is like the CVR basic concept is you do not want to jeopardize your equipment by saving the energy or power consumption.
Professor Sauer would argue his light bulbs are burning cameras. That's sure not. Desiree's got the data on his house. We want to know for sure. I guess he is consistently higher. But yeah, you don't want to burn stuff out faster, I guess. So. But I mean the whole thing is we would not go outside of the range. And, at the household level, it's 114 to 126 is the range. So it should, you should stay in that, we would stay in that range. But whether, if you're at 114, it changes the life one way or the other compared to 1.6, I don't know.
Yes, Professor.
The other nice follow-up, to tie this into power electronics, right?
Yeah.
It could be that your efficiency of your power converter could be marginally different between 114 volts and 126 or something like that, right? And then essentially, it's a step down. If you have to do a little less step down, sometimes it's very dependent on the power converter quality, but I can see there be a small percentage change in efficiency, perhaps.
In power electronics.
In aggregate, who knows what that would do. But I mean, the interest is actually to do a study of a few different power converters for residential use, for instance. Are their efficiency different at these different voltages or not? That is that.
Cool. Thank you.
Yeah, we had one professor, not at this university, he did all these tests on appliances at different voltage levels. And I asked him, where did you get all those appliances from?
I know the story.
He said he